So I've done my rant about how this should be called the law of conservation of energy. It deserves majesty. It deserves respect. What is it? It's a fundamental law of the universe. It says the energy of a closed system is neither increased nor decreased in any process. Let me talk about what's meant by a closed system. In fact, you might even underline that phrase. Owen, a closed system has no outside sources of energy. You're not plugging it into the wall if it's electrical. You're not adding gasoline if it's a closed system. You're not changing the amount of energy. The law of conservation of energy says this: the amount of energy in a system remains constant. You can transfer energy from one form to another, but the total remains constant. If you want to say it poetically, when the Big Bang occurred, the amount of energy in the universe has remained constant ever since. No new energy, no less energy. It says Mr. Dueck has a good demo for this. I'll show that a bit later. Philip, you'll thank me. So let's prove the law of conservation of energy. According to the work energy theorem, if we have a closed system with no outside sources of energy, so Owen, no plugging in, no adding gas, no outside sources of energy. If it's a biological, no eating food, we get no useful work. So the work energy theorem said this: work equals the change in potential plus the change in kinetic. But if it's a closed system, you get no useful work. So I said, now let it equal to 0. Oh, and you know what? What's change in anything? So I'm going to write it as PE final minus PE initial plus KE final minus KE initial. And then, Peter, all I'm going to do is plus this minus to that side and plus this minus to that side. And we get the law of conservation of energy. We get this: initial plus initial equals final plus final. What you start with is what you end with when it comes to energy, as long as you're not adding outside energy sources, as long as it's a closed system. You'll often hear me say, the energy's got to come from somewhere, the energy's got to go somewhere. It can't magically appear, it can't magically vanish. We can even be a bit more accurate if we want to include heat lost by friction. So I gave you, I think, this one on your formula sheet. If you want to, on your blue sheet where you're allowed to make extra notes, you could say, when we include friction, it's initial plus initial equals final plus whatever's missing must have gone into heat. And that's a more accurate version of the law of conservation of energy. A great example of this, I'll bring the notes back in a second, is a skateboard half pipe. So here's a half pipe. Right now, I've got friction turned off. I'm going to lift this girl. When I lift this girl, what kind of energy am I giving her? Gravitational potential. I'll put her right there. Is she moving right now? Be stupid obvious. So all of the energy is potential. And you can see the total energy is the little yellow bar. When I let her go, what's going to happen? Notice the total isn't changing. What's changing? How much of each is kinetic and potential? In fact, I can make some predictions. At the bottom, what will her potential energy be? So what is all the energy? What type? So I'm going to ask the same question. I'm just going to phrase it differently. Where will she be traveling the fastest? That's Y. How fast will she be traveling at the top? More specific. Right? Why? It's all turned into potential. There's no kinetic energy left. Now, right now, I've got friction turned off. This is not realistic. In real life, there's friction. So I'm going to turn friction on just a little bit. And what you're going to start to notice is another bar starts to creep up. Thermal or heat. Is the total energy changing, Manat? Nope. That's what the law of conservation of energy says. Whatever you start with is what you finish with. It can get transformed from one type to another. So if she doesn't add energy, she'll come to a stop. It's the same, by the way, instead of a half pipe, if you don't skateboard, a swing set is the same idea. When you're a little kid, oh, we got someone coming in late. Pause the video for a second. You were all toddlers, or if you've ever babysat a toddler and you take them to the park and you put them on the swing, all they know how to do is sit. Well, do you guys still call it an underduck? It was called an underduck when I was a kid, when you went underneath them and put, do they still call it? You know, that well, hasn't gone out of fashion? Oh, thank God, I feel so young. So you can give the kid a push, but they haven't learned to add energy to the system. And so because they're dealing with air friction, they'll slowly come to a stop. And then when you're about 4 or 5 years old, either your parents or one of your friends teaches you the magic of being on a swing. What do you learn? I'm going to make the assumption every one of you has been on a swing set. I hope so. If you haven't, you've missed out. What do you learn? How can you make the swing go higher without someone pushing you? Yeah, Caden. Okay, so you learn to tuck your legs at a certain time when you're going on the way down, kick your legs and lean back and pull on the chains. What you're doing now, it's no longer a closed system. You're adding energy to the system from your body. For a skateboarder who's on a half pipe, by shifting their weight at the right times, they're no longer a closed system. They're adding energy back to the system that's coming out of the food that they eat. So skateboarding would be exercise. Swing set would be exercise. Your body would be losing chemical stored energy as food, transmitting it to the system. So a skateboard half pipe is a great example. I got another really nice example as well. Some math with this. Example 1, a projectile is launched straight up into the air. If it reaches a final height of 93 meters, what was its initial speed? Use energy to solve this. Now, I gotta be honest, if they didn't say use energy to solve this, I would use kinematics. I would say VF equals 0. I would say VI equals question mark. But they said use energy, so I'm gonna use the law of conservation of energy. I'm going to write KE initial plus PE initial equals KE final plus PE final. Now, KE final, or sorry, KE is going to be 0 when we are at rest. So let's visualize this projectile. Is there ever a moment when it stops? Is there ever a moment when it rests? And I think what we're visualizing, if this is the ground, I think initial is right here. I think final is right there. Is there ever a moment when it's at rest? So I can say that's going to be 0 because you stop for a split second at the top, Tori. I agree. Now, PE is going to be 0 on the ground. Are we ever on the ground? And if so, initial or final? Yeah, PEI it's a 0, right? Prince Edward Island, not a real province. So we get, oh, what's my equation for kinetic energy from your formula sheet that you have out in front of you? KE equals what? Did I pick on you because you just yawned? Maybe. So it's going to be a half mv initial squared equals, what's my equation for gravitational potential energy? mgh final. Oh, is there an m in the left-hand term? Is there an m in the right-hand term? Is there an m in everything? Well, then it turns out the m's will cancel. They want me to get the VI by itself. I could divide by 0.5. I'm actually going to times by 2 times by 2. I'm going to actually clear that 1/2. I'm going to clear the fractions. And I get this. VI squared equals 2GH final. VI what? Squared. How do I get rid of a squared, Graydon? You back with me? So it's going to be the square root of 2, not negative 9.8. We're in scalarville, so just 9.8 times the final height. What was the initial launch speed? Now's the time when you want to go to your calculators. And that, what'd you get? 42.7. Anybody else? Really? Okay. Now, let me be clear. Don't write this next bit down. I'm going to do a whole bunch of writing. I could have gone, don't write this down, VI equals question mark, A equals negative 9.8, VF equals 0, D equals 93, and then I would have used VS squared equals VI squared plus 2AD. I would have said VI squared equals VF squared minus 2AD square root. And I kind of get the same thing. There's the 2. There's the 2. A, here it's negative 9.8. Here it's positive, but I'd have a minus minus, which would make it a plus anyway. You end up with the same thing. I would probably not use work or energy to solve this unless they made me, and they said use energy, so I did. So I wrote here, we could use kinematics to solve the above equation. I probably wouldn't. The law of C of E, that's my abbrev for conservation of energy, is really shines when you notice there's a change in speed, a change in height, and especially when there's a yucky curvy path, or when they talk about heat being involved. In other words, roller coasters, baby. I love example 2. I love example 2. Example 2, will you marry me? I'll just be really blatant. There's going to be one, no, you know what? There's going to be 2, no, probably 3 roller coasters on your test, at least 2. I love roller coasters, and conservation of energy lets me analyze them. It says a roller coaster car is traveling at 22 meters per second. If the car starts out at a height of 12 meters, how fast will the car be traveling when it gets to ground level? I'm going to gulp. I'm going to say it probably looks something like this. And we'll start the car right here. I'm going to call initial right here, final right there. Braden, looking at this roller coaster, will there be a change in height? Will there be a change in speed? Is it a yucky curvy path? This is a job for the law of conservation of energy. Let's add a few more things. It says that V is 22, and I guess that's VI since it's sitting by initial. It says this height is 12 meters. Okay. So if they gave me this question out of the blue with no instructions, I would say, hey, change in height, change in speed, yucky curvy path. I would go, okay, K E initial plus P E initial equals K E final plus P E final. Are any of these 0? Where is kinetic energy 0 when we're at rest? Are we at rest, Braden, at the very top initial? Are we at rest? It's obvious. 22. Are we going to be at rest at the bottom? No, in fact, you know what? I can tell you VF is going to be bigger than 22 because I've been on roller coasters and you go faster at the bottom of the hill. So if I got an answer on my calculator less than 22, I know I will have messed up, right? Okay, potential energy is 0 when we're on the ground. Braden, are we ever on the ground? And if so, where? What are we calling at the end? The word you're looking for starts with letter. Thank you. Okay. Manat, what's the equation for kinetic energy? So a half mv initial squared plus, what's the equation for gravitational potential energy? So it'll be mgh initial equals a half mv final squared. Braden, do you like roller coasters? Have you gone on roller coasters before? Cool. Braden, is there an m in the first term? Is there an m in the middle term? Is there an m at the last term? Is there an m in everything? What does that mean, folks? What's going to happen to the m's? Braden, you've gone on a roller coaster before? before you got on the roller coaster, did they make you step on a scale? Did they have to spread out heavy people and light people to make the roller coaster go? Can little kids and grown-ups go on the roller coaster regardless of their mass? Why? Because mass cancels. If that didn't, you'd have to step on scales. Oh, will an empty coaster car and a full coaster car still make it through the track? Yep. Now, what are we trying to find, Braden? Yeah. You could divide by 0.5 and then square root. I'm going to do something a bit different because there's a 1/2 and a 1/2. I'm going to actually multiply everything by 2, the first term, the middle term, and that term. Because when I do that, the 2's and the 1/2's turn into 1's. And I get this, vi squared plus 2g h initial, and if you don't mind, Braden, I'm going to put the vf squared over here by itself. And what I've really just done without even trying, don't write this next bit down. Can you see I've just derived vf squared equals vi squared plus 2ad, because g is the acceleration, that's the distance. It kind of pops out of there. So I usually, to clear the 1/2's, you can divide by 0.5. I usually multiply everything by 2 because it gives me a cleaner equation. And then final step, Braden, how to get rid of a squared. VF is going to be the square root of 22 squared plus 2 times 9.8 times 12. 12 meters isn't that big a height for a roller coaster. It's okay. I don't think we're going to be going significantly faster. I bet you we'll still be in the 20s. I don't think we're hitting 30 or 40 meters per second. But I could be totally wrong. I was doing a bunch of rough math in my head. Braden, what'd you get? 26.8? That was kind of ballpark what I was going to think. Is that right or not? I need a nod. I got a couple of nods. Yep. Okay. When we do go to Playland in May, and I have booked the trip, if you choose to analyze the roller coaster, that would be how you would figure out how fast you're going to go at the bottom of the first hill. You'll have to use some trig to estimate the height of the first hill. You'll have to do a little bit of math to roughly estimate how fast the car is coming over the first hill, and then you can figure out how fast you'll be going at the bottom of the first hill, and I think that just adds to it, in my opinion. Example 3. An 18-kilogram object is dropped from a height of 40 meters, and it strikes the ground with a speed of 25 meters per second. Sebastian, what's example 3 want me to find? How much what? You're right. Okay, I'm visualizing this. We're dropping an object. Is there going to be a change in height? Yes. Is there going to be a change in speed? Is there a yucky, curvy path? No. But did they mention heat? That's why I said when heat is involved, we're going to use conservation of energy, G. We're going to tweak our equation ever so slightly. Now we're going to say K, well, initial plus initial equals final plus final plus heat. And then I always pause and I ask, are any of these 0? Kinetic energy will be 0 when we're at rest. More specific. Initial or final? If we're dropping, VI is 0. Hopefully your teacher taught you that last. Oh, he did. Okay. Potential energy will be 0 when we're on the ground. What are we trying to find? Get the heat by itself. Yeah, this is a weird one, and I haven't figured out why. Because it's pretty clear. It's Ke plus heat. I see kids divide sometimes. I don't know why. And I haven't figured it out. It happens often enough that I've even tried thinking about maybe if I change the order that I write the terms, will that correct that silly mistake? I don't know. But anyways, I agree with you. Heat is going to be the initial potential energy minus the final kinetic energy. Hey, Manat, you're on. Heat is gravitational potential energy equation. And initial, so initial. Sebastian, is there an M in the last term? Is there an M in the middle term? Is there an M in the heat term? M does not cancel this time. If you're not sure if the M cancels, leave it in. You'll be fine. But I like to show you where it does when it does, because I think that explains interesting stuff. So let's plug in the numbers. I've scrolled completely down. What was M, Sebastian? G, 9.8. H, 0.5 times 18. Was VF 25? If you run the numbers without counting heat, without counting air friction, I think it would have hit it like 28 or 29. So we did lose some energy to heating up air molecules. Air friction is how we could think of that. What do you get? 1,400. I'll go 1,430. Just my usual 3 sig figs. Yeah. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. So, honey, what's example 4 asking me to find? Give me the first 3 words, kiddo. Work. This is not conservation of energy. And by the way, if the question doesn't say how much work, then don't use work energy. It's a common one of the things kids struggle with is they're not quite sure how to start. So I'm going to tell you if it says how much work, don't write this down. My first thought would be what Owen said at the beginning of class. It's F applied times distance. But Owen, do you see a force in newtons anywhere in this question? No. Do you see a distance in meters anywhere in this question? Nope. And so I would say, nice try. Back to Suhani. My next thought would be, hey, maybe they gave me the area of a force versus distance graph. Did they give me a graph? Be stupid obvious here? No. Then I would say, okay, time for the work energy theorem. What's the work energy theorem? So on your formula sheet, it says W equals, yeah. Now the change in potential, delta PE, that will exist when the question gives you some kind of a change in height. This question, if I gave this to you on the test, which I know on some of my versions it's there, I included the phrase something like over a horizontal road or over a level road or over level ground. We're going to have to assume that in this example, but on a test I would make sure that was clear. We're going to say, I think we can say it's 0. I don't think there's any change in height. Speaking of change in, what's change in anything? Well, what's change in anything? Minus initial. And here, I got to be fussy. It's not going to be VF minus VI. It's going to be a half M VF squared minus a half M VI squared, right? By the way, what don't I like about this question? You see it? Caden. Yeah, we got yucky units. You could convert on the side. Lazy but organized, folks. This is how I would do it if I wanted to do this in one complete step. I would go like this. Oh, first of all, Suhani, is there an M in the last term? Is there an M in the middle term? Is there an M in the first term? Do the M's cancel here? Yeah, it takes more work to stop a logging truck than it does to stop a motorcycle. Which, yeah, more energy. Okay. It's going to be work equals 0.5. What was the mass? 1,200. What was VF? 50 divided by 3.6 all squared. There's our conversion. Minus 0.5 times 1,200 times 80 divided by 3.6 all squared. If you wanted to do this in one step on your calculator, that's how you would do this. And I know some of you do like to, oh, if I can do it in one step. Mr. Dueck, that's just you that obsesses over doing it in one line. Fine. I like to do this in one step. I have no idea what the answer is. I think it's going to be fairly big. In fact, my just of some very rough math, I think it's going to be in the hundred thousands of joules. But negative. Typo, Mr. Dueck. Oh, typo, Mr. Dueck. You get negative 180,550. You know what? The fives repeat. If you didn't get that, don't clear your calculator. You can raise your hand and I'll come and look over your shoulder. Pause the video for a second. Go negative 181,000 joules. Why negative? What's the significance of the negative? For this vehicle to slow down, what? It has to what energy? Lose. Now the law of conservation of energy. Oh, first of all, B says, what force does the work? So here's the first question. We just did part A. Part B. All right, what force does the work? What force slows cars down? And ironically, the same force makes them speed up. Yeah, you can't drive on ice. So this is friction, and what that means is this energy transfer is going to manifest itself as what? Part C says, where do you think the energy is transferred to? Yeah, heat is the work done by friction. Unless you have a hybrid or electric vehicle, then most of that massive amount of energy is transferred into recharging the batteries through a regenerative system. How does that work? We'll get to that in May. We will, I hope. We'll talk about how that works. You'll learn every electric motor is also a generator, and every generator is also an electric motor. It just depends where you attach or the energy source. Gonna skip example 5. It's kind of cool, but it's a little lengthy. Example 6. Turn the page. Mr. Dueck, are we going to get to vote again? Yes, Owen. Yes, we are. It says this: 3 projectiles, A, B, and C, are fired from the same machine on the moon with the same initial velocity. Why on the moon? So we could ignore air resistance. That I could have done it on Earth and just said ignore air resistance. I dream of going to the moon, so we're going to be on the moon. Their paths are labeled A, B, and C. At location 1, that's here, that's here, that's here, which projectile will have the biggest kinetic energy? We're going to vote. Once again, how you hold your hand up, as I'm sure you are of the answer. So which projectile will have the biggest KE at location number 1? Let's see. Who says, Mr. Dueck, A, it's the highest, so clearly it's going to have the most kinetic energy because they had to have that to go that so high. Nah, it's B, because it's 45 degrees. That's the best one. I got one. Is that a vote? Nope. No, it's C. 1, 2, 3, 4, 5, 6, 7, 8. No, they're all the same. Duh. 1, 2, 3, 4, 5. Ah, we got a little controversy here. Convince me. Yeah. Okay. Connecticut, you're saying they're at rest? I don't. Vy is 0. Is Vx 0? They're still moving. If you got hit, it would hurt. Convince me. I think your argument is, new word of the day, specious, which means false. Convince me. Remember the skate park? Remember the skate ramp? Here we have the most gravitational potential energy. What's the smallest then? Kinetic is the smaller. Here, some gravitational potential, some kinetic. Here we have the least amount of potential energy because we have the smallest height. Well, then where is all the energy being manifested? Where is it shown up? Yeah, yeah. Smallest PE means biggest KE. Is that okay? Lower height, then it's all kinetic, or mostly kinetic. Okay, similar, same situation. Pat, location one. Which one has the biggest total energy? A, B, C, or all three will be the same? Who says A? Who says B? Who says C? Why is it all three the same, Philip? Okay. Look at them. Look at the starting location for each of them. What was their initial potential energy? Just look at the picture. What's the initial potential energy for all three of them? Where did they start? On the, where did they start? So what's their initial potential energy as a number exactly? Okay. And did it say they all have the same velocity, initial velocity? So what was their initial kinetic energy compared to each other? The same. What was their total energy at the beginning then? The same. And remember that yellow bar in the skate park? That means it's the same all the way through. All three will be equal. Started with the same. I'm going to use TE as my brief for total energy. That's going to be the same all the way through. And in fact, that's your answer to part C. It's going to be the same even at location 2. They're going to have the same total energy everywhere. Everywhere. No matter where on the path. Why? Because they started with the same energy. Now, some of it may be potential, some of it may be kinetic, but if you add them up, it'll be the same for all of them. Okay? So now, if you wanted to, you could underline same initial velocity, and you can make a little note here. Same KE, because that's the key to doing this. It's starting out with the same KE initial. PE initial is 0. They start out with the same total energy. It's going to be the same all the way through. Is this example 8 the last one? Yes, it is. No. 2 more. Okay. Example 8. I like example 8. I like example 8. A car at rest. I would probably underline the phrase at rest. At the top of an incline 3 meters high and 30 meters long is released and rolls down the hill. What is its speed at the bottom of the incline if the average friction force is 200 newtons? I'm going to gulp. Here's my car. I guess initial is here, final is here. This is 3 meters. And then this distance here is 30 meters. Jericho, what do they want me to find? Did they say speed or did they say velocity? That already suggests to me a scalar approach because they asked me to find a scalar value. Okay. In this question, is there a change in height? Is there a change in speed? You're going down a hill. Will your speed change? Yeah, don't overcomplicate. So ready? Is there a change in height? Is there a change in speed? Yep. Is there a yucky curvy path? No. Does this question mention heat? Kind of. Where? Friction's going to generate heat. Okay? So you know what this is a job for? Conservation of energy, GG. I'm going to write next to this so I can keep this all on one screen. I'm going to say, okay, it's going to be kinetic initial plus potential. Initial equals kinetic. Final plus potential. Final. And since they mentioned this, plus heat. Where is kinetic going to be 0 when we are at rest? Are we ever at rest? And if so, initial or final? Ah, where will gravitational potential be zero? On the ground. Are we ever on the ground? And if so, initial or final? Yep. What if they aren't zero? You'd be doing a lot more typing on your calculator, but it's not that big a deal. Uh, which of these three terms contains V final? So what do I want to get by itself? The KE final. I'm going to minus the heat over. So I'm going to go like this. I'm going to do two steps at once. MGH initial minus heat, and that equals a half MV final squared. Problem. Oh, first of all, Jericho, is there an M in the first term? Is there an M in the middle term? Is there an M in the heat? No. Okay. I'm going to divide by 0.5 M. I could go times by 2, times by 2, times by 2, but there's only the 1/2 to get rid of. So I think it's going to be easier to go. And I have this. VF squared equals, on the top I have MGH minus, I'm going to leave the heat blank for a second. I have 0.5 M. What we need to do is we need to figure out what the heck the heat is. I'm going to give you another definition of heat. If you want to, you could also add this to your blue sheet, not to your yellow formula sheet. Heat is the work done by friction. And Owen, we're coming full circle back to you. Work is what times what? Sorry, just don't say applied, just force. So the work done by friction, it's not force applied times distance, force of friction times distance. Heat is the force of friction times distance. Now, if I really wanted to make this nasty, Braden, I could have given you the theta degrees. I could have given you mu. You could have gone components. You could have said friction is what times what, mu times the normal force. Wait a minute, they gave me the force of friction. Woo! So let's continue on. It's going to be the force of friction. I've scrolled down, Jericho. What was the force of friction? 3,000? That was the force of friction? Sorry? Okay. You were doing the math and getting ahead of me. Times the distance. Now, which distance am I going to use? The 3 or the 30? It has to be in the same direction that the force is acting, which is going to be the... Yes. Oh, and as always, I can ask you to get any of these by itself if I give you the rest of the values. I could even give you V final and ask you to find the force of friction if you knew how long the hill was. Okay. Oh, and then how do I get rid of a squared? Square root. Let's write out the numbers, Jericho. I've scrolled way down. What was M? M was 3,000? What are the units next to that 3,000? So is that a mass? In fact, what is this? That's mg, right? Newtons. What do we call that? Not mass. Starts with the letter W. No now. What do they call it? No now. What are they? Yeah, weight. Okay. They gave me the weight. So you know what? I'll put it in for mg. H. Yeah, now you're back on track. Minus 200 times 30 divided by 0.5. Oh, if I know the weight is 3,000, how can I find the mass in kilograms? And I'm going to be lazy, Tori. I'm just going to go 3,000 divided by 9.8. For me, on my calculator, I'll probably type what's inside the square root first, and then I'll go square root answer button. Those of you that have the fancy smancy fraction buttons can probably make it look a little cleaner. But I'm going to go brackets around the top. Brackets around the bottom. Square root answer button. You're going to get 4 point something. So all of you should try typing this in. One of the things I find, the expressions here, they're not complicated, they're lengthy, and I see a lot of dumb typos on the test. So you want to get them out of your system, figure out how to type these in successfully in class. Is it 4.43? Is correct, I'm pretty sure. Yeah? Philip, is Graydon even able to see the screen with your backpack right in his face? You can? Philip, can you move the backpack? Because also I see Graydon's head nodding behind the backpack occasionally like he's trying to stay awake. Thanks, kiddo. Last one. Oh, I got a video to show you. That's right. Put your pencils down, look up. This is from MIT. This is a nice little setup. So what I'm arguing with you, or what I'm saying is the path doesn't matter for work and energy. If we drop something straight down, it should have the same speed when it hits the ground as if it swings down on a swing. So we've got two photo gates. They're identical photo gates. We're going to drop a ball from up here. We're going to drop it vertically and see how long it takes to go through the photo gate. Then we're going to swing it down on a swing. Ideally, it should have the same kinetic energy, the same speed, the same amount of time. So here's the vertical drop. Look up. 0.0091 seconds to go through the photo gate. So that's to 4 sig figs. Well, to 2 sig figs, but 4 decimal places. Now, we're going to put that same mass on a string. It's starting from the same height, so same amount of potential energy, gravitational potential energy. If it swings down, it should also be the same kinetic energy here, should be the same time to go through that identical photo gate. 3, 2, 1. Bang. Work and energy are scalars. The law of conservation of energy works for scalar math, which is nice. Last one. We're going to skip part A. We're just going to do part B because it's a roller coaster and I like roller coasters. Okay. Caleb, what does part B want me to write? A work/energy. Okay. First of all, did this question say how much work? In other words, do you see the word how and the word much and the word work? I'm already thinking I'm not going to be starting out by going work equals change in plus change in. Is there a change in height in this question? Is there a change in speed in this question? Is there a yucky curvy path? I think I'm going to say this. This is how my brain would handle this. Yeah, no, yes. Okay? I'm not going to write a work equation. I'm going to write an energy equation. And again, I'm going to do it beside so I can keep this on one screen. I'm going to go KE initial plus PE initial equals KE final plus PE final. Caleb, do they want me to include heat? And how do I know? Why? Oh, they want me to find the heat. Okay. I'm going to get the heat by itself. First, though, are any of these zero? Kinetic would be zero if we're at rest. Oh, you know what? I'd probably do one more thing. Owen, I would probably go, you know what? That's initial, that's final, just so I know what my brain is thinking. Yeah? Yeah. Are we ever at rest? Are we ever on the ground? Where? Get the heat by itself. How? Yeah, subtract. This is another one where for some reason kids like to divide. I haven't figured out why. So the heat is going to be, I'm not going to write this, look up, I'm just going to say it out loud. We're going to skip a step because I've been talking for a while. It would be KE initial plus PE initial minus KE final. Manat, KE initial. I'm going to go straight to this step. VI squared plus initial minus final. Are the masses going to cancel here? So, Braden, I fibbed a little bit. In real life, all roller coasters do have a little bit of friction. In real life, the masses don't cancel, but what we do is we grease the coasters down so that that energy loss to friction is negligible. So an empty car and a full car will make it through, so the masses are nearly canceling. That's what we do. It's just going to be plug and chug now. It's going to be the heat equals 0.5 m. Did they give me the mass? Oh, at the top, what was the mass of the car? 1,000. V initial, 2, don't forget the squared, plus 1,000 times 9.8 times 10 minus 0.5 times 1,000 times 12, they told me in part B, squared. Okay. What do you get? It's funny, you can't see, but all class, I've seen everybody at their desk every so often picking up the little heat pack. Oh, so warm, Peter. Oh, yeah, I know. What'd you get? Peter, what'd you get? Even? Really? Oh, you know what? There's a bunch of thousands in there. It probably would, actually. Sure. That's a fluke, but we'll take it. By the way, how long is the track? I could figure out the average force of friction because remember, this is the work done by friction, which is the force of friction times distance. If you go on your answer button, can you go 28,000 divided by 17.5? That would be the average force of friction. Why average? Because the angle is changing. That mg parallel and mg perpendicular would be changing as the angle is changing. I need calculus to find the force of friction at any one location, but I can tell you the average force of friction. That would be a nice hint follow-up question. We're done. What's your homework? Try number 1, but I need to explain number 1. I actually assigned this to you last year as well, but it's a good repeat. It says mechanical energy is just potential plus kinetic. In other words, here at location 1, what's the potential energy exactly as a number? So, honey, I know that I can find a half mv squared. That will also be your mechanical energy. That's your total energy. That's what this has to have everywhere. Then when you're here, you can figure out what your potential energy is, what must be left over for kinetic, what V has to be. See if you can figure it out. 1 is good, 2 is good, 3 is good, 4 is good. You can skip 5. Ha ha ha. You can skip 6. Ha ha ha. I like 7. I like 7. You can skip 8. Yeah, 9, 10 is good, 11 is good. You can skip 12. You can skip 13. You can try 14. You can try 15. That's a fair bit, I realize. There's going to be a lesson where we're going to slow down in a little bit, but I really want to try and get this test in before the Christmas break. Thank you all for your patience.